Charles' law relates volume and temperature. The volume of an ideal gas is at absolute zero, minus 273 degrees Celsius. Real gases condense at their boiling point, so it's not visible or possible to have a gas with zero volume. The gas laws are based on the Kelvin temperature. So all gas law problems must be worked in Kelvin. Anytime you plug a number into any of these equations, you first have to convert it to Kelvin. So Charles' law says that volume and temperature are directly proportional. So as volume increases, temperature increases. As temperature decreases, volume decreases. So this problem, we have some temperatures here, and then we have the volume here. So we have volume 1, T1, T2, and we're trying to figure out volume 2. So with V2, we're unsure, but with these temperatures, we need to convert them to Kelvin. So how do you convert them to Kelvin? If you look at your chemistry aid sheet, you can see Kelvin is the degrees Celsius plus 273. So before we put these in, we have to add the 273. So 25 plus 273, 298. And negative 15 plus 273 is 258. So now we can plug it into the equation. V1 is 2, T1 is 298, and we're going to set that equal to V2, which is something we don't know. I'm just going to use the letter X, over T2, 258. Now for this one, we can cross multiply. So we can do 2 times 258 is equal to 298x. And now we can solve for x. And we get 1.73 liters. The volume of a gas always increases when temperature increases and pressure decreases. So volume and pressure are inversely related. When one goes up, the other goes down. But volume and temperature are directly related, which means that when one goes up, the other one also goes up. A sample of CO2 has a volume of 200 mils at 20 degrees Celsius. What will be its volume at 40 degrees Celsius? So go ahead, pause the video, and work through this one, and then we'll work through it together. Okay, so if you recall, we have to convert these Celsius to Kelvin. So 273 plus 20 is 293. 273 plus 40 equals 313. So we have our V1, T1, T2, and we're looking for our V2. So V1, T1, 200 over 293 equals V2, T2. We can then cross multiply 200 times 313 is equal to 293x. And then we can solve. And we get 213 mils. A sample of gas has a volume of 3 liters at 10 degrees Celsius. What will be its temperature in degrees Celsius if the gas expands to 6 liters at constant pressure? Go ahead and pause and work through this one. Okay, so we have to convert this to Kelvin. And we have our V1, T1, V2, and we need our T2. So we have 3 over 283. We're going to set that equal to 6 over x. We are going to then cross multiply. 3x equals 283 times 6, and then we're going to solve for x. 283 times 6 divided by 3 gives us 566 Kelvin. But then we have to convert that to degrees Celsius because it's asking for the answer in degrees Celsius. So to convert it, we would subtract 273 and we get 293. Gay-Lussac's law compares pressure and temperature. As one increases, the other also increases. So these are directly related. As pressure goes up, temperature goes up. P1 and T1, P2, T2, very similar to the volume ones, so we won't actually go through any examples of this, but you may encounter a problem like this on a test. So when you encounter a problem, you need to determine what types of information are provided to you in the problem and what it's asking for. If they provide you information about pressure and volume, and they're asking for what the volume would be if you change the pressure, and it's just referring to pressure and volume, you know you can use Boyle's law. If the problem presented to you talks about pressure and temperature, you know that you're going to use Gay-Lussac's law. And if it presents to you volume and temperature, you know that you're going to use Charles' law. Combined gas laws is if it gives you pressure, volume, and temperature, and it changes 2 of those variables. It combines the Boyle's law, Charles' law, and Gay-Lussac's law. All of these equations are written in your chemistry aid sheet. So P1, P2, V1, V2 can be any units as long as they are the same. T1 and T2 must be in Kelvin. So if a sample of air occupies 500 mils at STP, what is the volume at 85 degrees Celsius and 560 torr? So first of all, we need to define what STP is. STP is standard temperature and pressure. Standard temperature is 273 K, and standard pressure is 1 atm. Since the problem gave us this in torr, 1 atm is equivalent to 760 torr. So we can use those as our starting ones. So now we have a V1, a T1, and a P1. Now, 85 degrees Celsius, we know we have to convert that one to Kelvin. So 85 plus 273, we get 358. And 560 torr, and we're trying to figure out what that volume 2 is. So this is T2, P2, and we don't know what V2 is. So now we're just going to plug the numbers into the equation. P1 V1, T1, and we're going to set that equal to P2, V2, which I'm just going to put the letter X for, and T2. Now what we're going to do here is cross multiply. So we're going to do 760 times 500 times 358 and set that equal to 273 times 560 times X. So then we do 760 times 500 times 358, and we get that number. We're going to divide away the 273 times 560 by putting that in parentheses, and we end up with 889.8, or to 3 sig figs, actually 2 sig figs because the pressure and temperature is given in 2 sig figs, we could round this to 890. And it's going to be a volume of milliliters. Okay, so go ahead and try this one, and then we'll work on this together. So pause the video, and then we'll come back. All right. So we're starting with 500 mils at 722 torr and 25 degrees Celsius. And to make this easier for us to figure out, I'm just going to write the variables here. P1, V1, T1, P2, V2, T2. So pressure 1 is 500 mils. Sorry, let me erase that. Let's start over. P1, V1, T1, P2, V2, T2. Now, pressure 1 is 722 torr. Volume 1 is 500 mils. Temperature 1 is negative 25 degrees Celsius. We're looking for T2, which I'm going to put an X next to. If the gas has a volume of 2.53 liters, and 491 millimeters mercury. Okay, so clearly we have some issues with units, which is why I wanted to write it out this way. So first of all, we look at the pressure units. It doesn't matter what unit we use as long as they match. Well, the good thing is that 1 millimeter mercury is equal to 1 torr. So we can just write this as 491 torr. Then we look at the volume units. We have 500 mils and we have 2.53 liters. I like working with smaller numbers, so I'm going to convert this mils to liters. And I'm going to do that up here. 500 mils, there's 1,000 mils in 1 liter. So when we do 500 divided by 1,000, we get 0.5 liters. And now this unit, the temperature unit, has to be in Kelvin. So we're doing minus 25 plus 273, 248 Kelvin. Now we can finally put this into the problem. So P1, 722, V1, 0.5 liters, over T1, 248, is equal to P2, 491 torr, V2, 2.53, over T2. We are going to cross multiply 722 times 0.5 times, we're going to just use x for the T2, equals 491 times 2.53 times 248. When we combine these together and divide away anything that's attached to the x, 491 times 2.53 times 248 equals, and then we're going to divide away the 722 times 0.5 in parentheses. (722 times 0.5), and I get 853. Now let me just double check that so I didn't make any calculator errors. (853) is what I get. So now they wanted that in Celsius. This is in Kelvin. To get to Celsius, we subtract 273, so we get 580 degrees Celsius. All right, you can pause the video and work through this one. Okay, a sample of gas, and we're going to write down our variables, P1, V1, T1, P2, V2, T2. Pressure 1, 700 torr. Volume 1 is 8 liters, and temperature 1 is 20 degrees Celsius. Volume is our X, standard temperature is 273, and standard pressure is 1 atm, or 760 torr. If you're wondering where the pressure conversion chart is on the chemistry aid sheet, it's on the first page, right where we have all of our common conversion factors. So you can see 1 atm is 760 torr, or 760 millimeters mercury. So our units look okay so far. We just have to convert this one to Kelvin. So 273 Kelvin, or 20 plus 273 gives us 293 Kelvin. Now we can plug these into the equation. So we have 700 times 8 divided by 293. We're going to set that equal to 760 x over 273. We are going to cross multiply 700 times 8 times 273, and we're going to set that equal to 293 times 760 times x. When we solve for x, we end up with 6.87 liters. Dalton's law of partial pressures. So when we start talking about blood gases in human health, we refer to the blood gases in human health as the partial pressure. So we say partial pressure of oxygen in the blood is this. Partial pressure of carbon dioxide in the blood is this. Partial pressure seems to be a scary term that nobody likes to hear about, but it's very simple. If I were to compare partial pressures to weight, let's say I have 3 kids. I have one kid that's 50 pounds, one kid that's 100 pounds, and one kid that's 150 pounds. I tell all 3 of them to get on a scale because we're going to go down one of those giant water slides at the water park, and we got to make sure that the weight isn't too much for those water slides. So I say, everybody go step on the scale. Now together, the whole weight is 400 pounds. But my littlest boy, my 50-pound boy, has a partial weight of 50 pounds. So out of the total weight, out of the 400, my little one has a partial weight of 50 pounds. My middle one has a partial weight of 100 pounds. And my big one has a partial weight of 150. Did I do that math wrong? Let's see. It's 300, not 400 total pounds. Okay, so the total weight then is 300 pounds, but each one of them has a partial weight. That's very similar to total pressure and partial pressures. So the total pressure of the gas consists of adding the individual pressures within the gas. So atmospheric pressure is the result of the combined pressure of the nitrogen, oxygen, and other trace gases in the air. So a sample problem would be a gas has a total pressure of 3 atm. And let me just add that to here, since there isn't a sample problem here. So gas has a total pressure of 3 atm. Gas A has a partial pressure of 1 atm. Gas B has a partial pressure of 0.7 atm. What is the partial pressure of the remaining gas? Well, the total pressure of 3 is equal to the pressure of gas A plus the pressure of gas B plus the pressure of that last amount. So now we just subtract these from 3. So 3 minus 1.7 gives us 1.3. So very simple addition and subtraction. Another sample problem would be gas A has a partial pressure of 1 atm, gas B has a partial pressure of 1 atm, and gas C has a partial pressure of 1 atm. What is the total pressure of the gas? In that instance, you just add them all up, and your total is 3. Okay, one last gas law before we get into gas stoichiometry, the ideal gas law. PV equals nRT. So PV, pressure and volume, is equal to N, which is the number of moles, R, which is a constant, 0.0821, and T is the temperature. So calculate the volume of 1 mole of any gas at STP. So standard temperature is 273. Standard pressure is 1 atm. So when you put any information into the ideal gas law, these have to be the units that you use. You have to use liters, atm, moles, and Kelvin, because our constant that's provided are in those units. So pressure, 1 atm. Volume, it's wanting us to calculate the volume, so we don't know the volume. We're going to put X. Equals the number of moles and that's 1 because it's 1 mole. R is our constant, so we're going to just put 0.0821. And T is our temperature, 273. So now we can solve for X. 0.0821 times 273 is 22.4 liters. At standard temperature and pressure, 22.4 liters will be our conversion factor between moles of a substance and liters of that substance, of the gas. So when we go on to gas stoichiometry, that is where that came from, that conversion factor came from. Okay, how many moles of argon are contained in 1.3 liters at 24 degrees Celsius and 745 millimeters mercury? So go ahead and pause the video and try to solve this one. Remember, your units have to be in liters, atm, moles, and Kelvin. Okay, so we have first to convert this to atm. Let me just write these down. P, V, N, R, T. Pressure was given as 745 millimeters mercury. Volume is given as 1.3 liters. N is what we're trying to figure out. R is 0.0821. And temperature is given to 24 degrees Celsius. So the first one we're converting to atm. 760 millimeters mercury is 1 atm. So when we do the conversion, 745 divided by 760 is equal to 0.980 atm. Liters is an okay unit, so we'll leave liters. This is our constant, we don't touch. But this one we have to convert to Kelvin. And we do that by adding 273. So 24 plus 273 is equal to 297 Kelvin. Now we can put it into our equation. Pressure, 0.980, volume, 1.3, equals X, we don't know, times the constant, 0.0821, times the 297 Kelvin. So now we are going to isolate the X. 0.980 times 1.3 divided by, parentheses, 0.0821 times 297, close the parentheses, and we get 0.0522 moles. Let me just double calculate this. Yep, that's what we get. Okay, Using the ideal gas law, it's saying calculate the molar mass of an unknown gas if 4.12 grams occupy a volume of 943 mils at 23 degrees Celsius and 751 torr. Using the ideal gas law, P, V, N, R, T. P for pressure is given as 751 torr. V for volume is 943 mils. N is our unknown. R is 0.0821. And temperature was 23 degrees Celsius. So we have to convert these to the correct units. First, we're going to convert this to ATM. So 1 ATM is 760 torr, so we do 751 divided by 760, and we get 0.988 ATM. Next, we have to convert this one to liters. .943 liters. Next, we have to convert this one to Kelvin. 23 plus 273 gives us 296 Kelvin. So we plug this in, 0.988 PV 0.943 equals NR0821 T 296, and we're going to solve for X. And X, we get 0.0383 moles. So if we want to know the molar mass, we can take grams per mole. So this is grams in 1 of the moles. And we're just going to multiply across the top. 0.158. So this is our final answer for grams per mole.